Bismillahirrahmanirrahim. In this video, we'll study about the design of a sequence detector having single sequence. So we will design the circuit so that any input sequence ending in 101 will produce an output Z is equal to 1. So this is the given sequence, inputs, all these values, and from here we write the output. And this is the time circuit. Now how to write output, let me explain it. Remember, we are looking for 101, so the first bit is 1. When we go here, we find x is equal to 0, so it's not the desired bit, therefore the output will be 0. Move next, x is 0, so output is still 0 because it is not the desired bit. Next is 1, so this is the desired bit, but it's not the complete 101 sequence, therefore the output will still be 0. Next, instead of 0 we have 1, so I think we'll now consider this to be the beginning of 101, but output will still be 0. Next we are getting 0, so this is the second bit of the sequence, but it's not the complete sequence, so output will be 0. Now next bit is 1, so this here the sequence is complete, and therefore the output will be written as 1. And we'll proceed same way to write the inputs, write the outputs. Wherever we get 101, we write an output 1, 101, output 1. So first of all, we write this manually, and then we'll design the sequence circuit. Now initially we do not know how many flip-flops will be required, so we'll designate the circuits as S0, S1. So like this is the state diagram. So this is one of the state S0, second state S1, third state S2, etc. So we start with the first one. We start with S0. From here we'll start. And this is called the reset state or starting point. And we'll follow this saying that don't move unless you get the desired bit of the desired sequence. So unless we get this bit, these bits, first of all we should get 1, then we'll move. Then after we have got 1, if we get 0, then we'll move. And after this we have got a 1, then we'll move. Else we'll stay where we are. So let's see how this happens. So the first case we are looking for a 1, the first bit of the sequence 101. In the question, at t is equal to 0, x is 0. So at t is equal to 0, the input x is 0. So we'll not move, we'll stay there. And how do we show this in the circuit? That is, we loop back. We are here, so we are staying in the circuit, so we loop back to S0. And this we had explained earlier, this shows actually the input x and the output z. So input we got x0 from here, and output was also 0, this 0. Therefore we'll write it 0/0. Next we come to T1 here. Here also input is 0 and output 0. We are looking for 1, remember. So we'll stay here, don't move. So we stay again, we loop back and come here. So just show one loop. The previous loop, you can say it has got eliminated. Now we have got x1 at t is equal to 2, x1 is received, but output is still 0. So since x1 we are looking for and we have received x1, therefore we'll move to the new state from here. Move to new state. So we are moving to a state S1. And what do we write here? The input from here you can see is 1 and output 0, so we'll write it 1 /0. And we can make a note that how we reached here. After we have got a 1, we have reached here. Okay, now we'll look for 0 because 1 has been received. Now we are looking for the middle one, 0, second one. So at t is equal to 3, we are expecting a 0, but we have got a 1. T3, expecting 0, but we got 1, therefore we stay there, don't move. So we loop back. As we said, we loop back and we write 1 as the input and 0 as the output from here. T is equal to 3, 1 input, 0 output. And we are still looking for a 0. We were here. Now at t is equal to 4, we got a 0. So since we got a 0, that is what we were looking for. Therefore, we'll move to the new state S2. So we'll write a new state S2 and we'll move to S2 from S1, and the inputs or the parameters written here x, y is 0 and 0. This 0 and this 0. So we are writing 0 and 0. Now we have reached here after we have got 1, 0. Now we are looking for a 1, 1, 0 we have got. Now we are looking for the third bit, that is the 1. And at T5 you can see we have got a 1, input 1, and therefore the search is complete now. 1, 0, 1 we have found. Now what do we do from here? Where do we go? The question arises where the circuit should then go, whether the circuit then should go to a new state or back to S0 or S1. So first of all, we'll see whether we can either be between the two. If we can't accommodate, then we will go to the new state. Now because this circuit is not supposed to reset when the output occurs, so the question has not given. Sometimes it is given, then that the moment you get this sequence, you reset or you start again. But it is not mentioned, so we'll not go to the reset. We cannot go back to S0. However, because the last one in the sequence at T5, this last one, can also be the first one in a new sequence. And so we can return to S1. So since this could also be the first bit of a new sequence, therefore from here we'll return to 1, where we return after we have got 1. We have reached from having 1, so this will move to get a 1 here. Okay, so now our drawing will be something like this. We have moved here. So we are here, and now let's see what to do. We are again looking for a 0y because now the next sequence we are looking for. So next sequence we have already got a 1 here, so we are looking for a 0. But at t is equal to 6 we have got a 1. So it's not what we were looking for. Therefore we stay there. So we're staying there again at S1. Next T7 we have got a 0. So this is what we were looking for, a 0. So we move to S2. Move to S2 again. So at t is equal to 8. T is equal to 8, we got another 0, which was not desired. We wanted a 1. So since there are 2 zeros, we have received 2 zeros in a row and must reset the circuit to state S0. So we'll go back to the reset state and we start again from here, because 0, 0 is not part of our desired input, therefore we'll reset. So this is how you draw the state diagram. So this is our complete state diagram. This one we move to the reset state when input was 0 and output was also 0. And this is called Mealy state graph, where we write xy. This is Mealy state graph. So now that we have drawn the state diagram, let's move into incorporating flip-flops, because that is what we need for designing the circuit. And a flip-flop design could be something like this, not exactly this, but we'll have two flip-flops because there are three states here. So at least two flip-flops we need, or exactly two flip-flops we need. And when we incorporate the flip-flops, then we'll change the name from S to S0, S1, etc. We'll now put the flip-flop states. So it could be 0, 0 for A and B, or it could be 0, 1 for S1, and it could be 1, 0 for S2, the third state. And now that we have incorporated flip-flops, we just need to now draw the what is known as transition diagram. Sometimes it is also transition table or state table. It's exactly same, no difference. In the state table we just write it S0, S1, but in the transition table we write AB for the two flip-flops. Okay, now the options we'll have, we had done this in the video number 1 also. So those of you who have difficulty, they can go to video number 1 and revise. Okay, now we used a shortcut name PINO, that is the present state, input, next state and output. Now the present state, as we saw, it will be 0, 0 or 0, 1 or 1, 0. So we have just written them. We have written them twice because x could be 0 or x could be 1. So we complete this table. Normally, 0, 0, 0, then 0, 0, 1, then 0, 1, 0. You write it like this. What is missing here is 1, 1. There is no 1, 1 because we only have 3 states. Okay, now based on this and this, what will be the next state? So let's see, AB 0, 0, that means we are here. And x is 0, so x, you can see this is the first one is x and the second one is output z. So x is 0. Then what we are getting? We're going back to 0, 0. That means A next will be 0 and B next will also be 0. So we write it like this. And then what about the output z? Now this is also showing the output. The second one is also 0. That means this is output. You remember this is x or y, x or z. So this is also 0, so we'll put a 0 here. And similarly for the this case, when both are 0 and x is 1, where do we go? Both are 0, x is 1, then we go to 0, 1. So the next state will be 0, 1, but the output is still 0. You can see it is 0. So based on this diagram, you can complete this table. This will be 1, 0, 0, and then all 4 states. I hope you can follow from this graph. Okay, so our transition table is now complete, and let's move next. So this was the table. Now we'll simplify using K-map. First of all, these are the 3 inputs, and this is the output we'll consider. So let's have a K-map. So this is our K-map. AB and X are the inputs, and then we'll fill in this K-map, and this I'll show you 1 or 2. So when AB is 0 and X is 0, that means this is 0 and this is 0. We are in this box. The output should be 0, so we put a 0 here. Similarly, 0, 0, 1, we put a 0, so 0, 0, 1, we put a 0. 0, 1, 0, so 0, 1 and 0, we put a 1. and the remaining 3 are zeros. Since we don't have 1 1 in this, therefore we'll put a cross, that is to mean don't care conditions. So these 2 crosses we have put, and now we can simplify. Now remember, this table was for the next state of A flip-flop, and A next state we write as positive A plus. So that is showing the next state. And from here now you can see the answer. We can write that A plus is equal to, what is this value showing? X dash, and this 2 are common, B common, so it is X dash B. And similarly we'll solve for the middle one, that is a B plus, and also for Z. Okay, so this is for B plus, and here we are getting the answer B plus is equal to X. And in the third case for Z, we'll get an answer including the don't care condition. Z is equal to XA. So we have now these 3 values, 3 equations. Design the circuit, so these 3 values, and let's now design the circuit. Okay. Now we are using D flip-flops, and I hope you know that D flip-flop has only one input, one output, and the A flip-flop will be now called DA, where D type of a flip-flop and A output, which is actually equal to A plus, that is this one, and which is equal to from here X dash B. And similarly DB is B plus X from here, and the output we can write Z is equal to XA. So we'll now use a circuit to implement this. 2 flip-flops, so 2 flip-flops, and some connections. How the connection is made, let's see that. DA is A plus is X dash B. So this output should be X dash B. That means the input should also be X dash B, because D flip-flop just transform the input into the output at the clock pulse. Okay, so what we are looking here is X dash B. So for that we have to use an AND gate with 2 inputs. So AND gate, one of the inputs should be X dash and the other input should be B. We got this input from the B flip-flop and connected, and to get X dash we take a signal X and use an inverter to get X dash. So X dash B is complete for the first one. The second one is B dash X. That means this here it should be X. So let's connect this to the X line, and the output is Z is equal to XA. So we will use an AND gate here also. A we connect with the A flip-flop, and X we connect with the X input signal. So this is the complete design. And if you want, if you have time, you can just take the value of X or the sequence that we had. We keep on implementing and keep following from here and see if you get the result. Or maybe you can use some kind of a simulation circuit to verify your result. So I hope this gives you an understanding how you can solve this type of a circuits. I'll try to implement more examples for this so you get a better understanding. Thank you.